What if I told you your soil is literally breathing right now? Not with lungs, with diffusion. And that invisible traffic of oxygen in and carbon dioxide out decides whether roots thrive or tap out. Quick subtitle: How Oxygen and CO2 Actually Move in Soil. Alright, Diffusion 101. Gas molecules naturally move from where there's more of them to where there's less, until everything evens out. No fans, no pumps, just the concentration gradient doing its thing. Now, the mathy version is called Fick's law. Don't bounce, I'll keep it simple. The rate of gas movement is proportional to two things. 1. How big the concentration difference is between point A and point B. 2. How slippery the path is, which we call the diffusion coefficient. Bigger difference, faster flow. Easier pathway, faster flow. In air-filled soil, oxygen pulls a little flex. Its diffusion coefficient in air is about 1.25 times higher than carbon dioxide. Translation: O2 threads through soil pores faster than CO2 can escape. So even as roots and microbes burn oxygen and spit out carbon dioxide, fresh O2 can usually hustle in fast enough to keep everyone happy. But then it rains. A lot. Pores that used to be full of air get filled with water. And here's the kicker: diffusion through water is thousands of times slower than through air. Imagine sprinting on a track versus slogging through a pool in jeans. Same legs, totally different outcome. So in waterlogged soil, oxygen can't get in fast enough. Meanwhile, carbon dioxide from root and microbial respiration piles up because it can't get out. Oxygen drops, CO2 rises, and boom, anaerobic conditions. Swampy smells, stressed plants, yellowing leaves, microbes switching to less efficient, sometimes toxic pathways. Back to Fick's law for a sec, because it predicts all of this. The concentration gradient is trying to help. There's plenty of oxygen above the soil and not much down where roots are. But the diffusion coefficient in water is so tiny that the overall rate crashes. Big gradient plus tiny pathway equals slow motion. A couple of real-world takeaways. Structure matters. Soils with a good crumb structure and connected pores let gases trade places quickly. Compaction is the enemy. Squished pores mean longer, twistier roots for gases. Drainage is clutch. After a soaking, you want water to leave so air can return and diffusion can sprint again. Organic matter helps aggregate soil, building those air highways. Here's a cool counterintuitive bit. Even though oxygen moves in faster than carbon dioxide moves out in airy soil, plants still do great because the system is open and always venting. The second you fill those vents with water, the whole gas exchange becomes a traffic jam. So the next time you think about healthy soil, don't just picture nutrients. Picture airflow. The quiet physics of diffusion, Fick's law in action, is the difference between a root that sips oxygen all day and one that's holding its breath. Let your soil breathe. It'll thank you.